in India. We look like we've lost a few of our India folks because it's gotten a later hour. So I'll turn it over to you.
Thank you. Is my screen visible?
Yes, it is. You're all set.
Okay, thank you. So continuation with my previous talk, this talk is mainly on the residential area energy management using demand side management. So if we look at the architecture of a residential area, it is a large distribution network, consists of capacitor banks and voltage regulators, PV panels, batteries, and obviously the residential customers like the smart homes. If we talk about individual homes, and multi-storied building, which is quite popular in urban areas now. And if we see the optimization techniques or the energy management techniques followed in most of the smart home or building techniques, that is, the first one is the identification tool, which I have described before. Now we'll move towards to the home energy management, that is basically for a single home. Then looking to this architecture of the overall residential area, then we can identify the energy management objectives for first for the home energy management, then second for the multi-story residential apartment building, where mainly different customers are residing under the one roof, though they are different, but from the utility point of view, that is a cumulative demand. But due to their different or several non-identical natures, so we cannot consider them as a cumulative load. So how to segregate them and how to manage those building loads properly. And the last one, obviously, the large distribution network energy management. So I will start with that real-time energy management at smart home, where the synergistic real-time source storage load dispatch model has been proposed in presence of battery co-located rooftop solar power panels, where the total objective optimization process is designed as a multi-objective platform where minimization of consumers' dissatisfaction is also considered with the monetary cost reduction objective. Then as it is a real time, so to consider the long-term benefits, the long-term benefits has been modeled as a time average stochastic optimization objectives. And finally, the overall problem has been solved by outer approximation method. So this is the proposed approach where three types of discomfort or dissatisfaction cost has been considered. First one is the visual discomfort to control the sum of the lighting loads in the home. The second one is the thermal discomfort to control the temperatures, indoor temperatures by controlling the power consumption of AC, air conditioners. And the third, which we have considered the total load demand of other loads, which has been designed as considering the Kano's model, customer satisfaction model, where the electricity is considered as a must-be requirement, which is a extreme requirement in our daily life. So I have modeled it as a must-be requirement with this exponential function. Then considering this multi-objective one, the reliability constraint is added to minimize the load shedding operation on the total load demand. And for subject to that, all the home appliance operating constraints, power balance, and the demand side management or demand response signal obtained from the local DNO. So for the solution process, first the overall problem is modeled as a mixed integer convex programming, which has been segregated in two sub problem. That is, first one is the mixed integer linear programming, which is the outer approximation algorithm, where the non-convex constraints has been modified as their linear constraint counterparts by taking a cut of the convex equations, and the sub problem, which is completely a convex problem. By solving this two problems iteratively with the help of outer approximation methods, where the upper problem, like the outer approximation MILP problem, will get the integer values of the decision variables, and the sub problem will give the continuous values of the decision variables. With this, the simulation has been operated with first with the single objective, where we can see that the top graph, which is the luminance control in case of a clear sky and overcast sky day. We can see in absence of the dissatisfaction cost, all the time the temperature is set to the maximum preference point, not at the preferable set point, at the maximum preferable point, and the illuminance level is set at the minimum preferable set point. And according to that, the power consumption of the lights and ACs has been varied over the day. But though it is a real-time process, but still we can see that the battery charging and discharging is happening depending upon the loads. Like when the peak demand is processing, like at the evening hours, then it is at the discharging mode, and when it is at the peak solar power generation hours, it is at the charging mode. Now moving towards to the multi-objective process, we can see that at the time when we consider this dissatisfaction one, we can see the temperature is mainly at the preferable set point, like which is the most comfortable temperature or the illuminance point for the customer. But somehow, sometime it is deviating when the monetary cost is exceeding the boundary limits, and to limit that one, that again the temperature or the illuminance is varying. And considering the daylight effects, when the proper daylight is available on the clear sky and overcast sky day from the windows, it is automatically turning off all the lights and saving the energy. So taking this comparative analysis between the single objective and the multi-objective case, we can see that obviously the dissatisfaction cost, inclusion of dissatisfaction clause will come in expense of more monetary cost. As you can see from the graph that as every time interval, the electricity bill or the monetary cost is obviously high for the multi-objective case. But if we compare this, our real-time technique with the standard greedy algorithm, where we don't consider the long-term benefits of our any decision, then we can see that our our solution process or our proposed methodology is giving lesser cumulative monetary energy cost compared to the greedy algorithm. Now moving towards the building energy management, where multiple residents are residing under the one roof of a single building at different apartments. Then here the distributed optimization process is proposed, where there will be a central building management system which is only responsible to keep the power balance inside the building, and respective dwellings or respective flats is responsible to manage its real-time demand. And the interaction between these two will be done in terms of Stackelberg game, single leader multi-follower Stackelberg game. And this is the overall architecture of the residential building, where each and every flat has been considered as a separate entity, and the overall building management system is considered as a local DNO for this building, and there will be a virtual energy trading platform between them, where the central building management system is taking the actual price data from the local according to the demand of the each flats. It will assign a virtual real-time price, which is not the used for the electricity bill. It is just used to motivate each and every dwelling residences to alter their load pattern according to the peak load or the energy price. So in this optimization process also, the dwelling unit optimization problem, where it will minimize the virtual payment to the CBMS, and also it will maximize the usefulness of its consumed power to maximize its benefit. And further, the CBMS is also has the responsibility to maximize its earning, like to minimize the total power purchasing cost from the local DNO, and it maximize the consumers, like every flat's owner's comfort. So the solution approach is done as it is mostly it is a non-convex programming. So for that we have linearized it or convexified it with the help of Lyapunov optimization process. And finally, the solution technique has been proposed with the help of Stackelberg game, where initially the initial game has been started with the central building management system, where it will take that real-time load, unaltered load demand of each dwelling unit, and then it will generate the virtual real-time price and convey it to its customers, like each flats, and getting those signal, each flat is responsible to alter its own demand and reply back to the CBMS if they have altered it. If they have not, then they will be penalized, or they will experience more virtual cost, which will at the next iteration, which will motivate them further to alter their total demand. And it will continue to do this iteration process until and unless all the residents, all the flats and all CBMS have nothing to alter in the next iteration. So this from the simulation results, we can see that if red is the in the top figure, if red is the actual real-time price, which is same for all of them, and if we consider four different lifestyle residences like D1, D2, D3, and D4, where D1 is the most flexible one and D4 is the most critical one, then with these, if we go, then we can see that due to the unequal assignment of different virtual energy price, D1 to D4, everyone is motivated to alter some of their total load demand at each and every time phase. And but the total time average load shedding percentage is always below the 50%, like 0.5 per unit, like which is the reliability constraint. And the battery charging and discharging is done according to the availability of solar power. Now, if we compare this with our standard centralized process, which is shown as a gray color in this in the right hand side corner graph, which is mostly followed if we take the overall building consumers as a single entity, then what will happen? We can see that D1, which is the most flexible customer, it is experiencing almost every time it is experiencing the load cut. But D4, due to its critical operation, it is not experiencing at all any load curtailment. That means it is quite biased to the customer, which is more critical, and it is doing injustice to the customer, who is flexible. Means who is helping to reduce the peak demand, it is forcing them to reduce it further, which is not a very good thing. So we can see that our technique is quite beneficial in this process. And the total solution time for this real-time optimization process for these four customers is 2 seconds. Now moving towards the real-time advanced energy management of active AC distribution network, where the customers are distributed in the all the nodes, and we are trying to minimize the total monetary cost of the overall network. So the topology behind this is to merge the conservation voltage reduction technique with the demand regulation or the demand response process to get an energy efficient operation for the whole network. So to do that, first the direct load control or the real-time load shedding process is merged with the CVR technique, and the overall optimization technique is simplified with the help of virtual queue theory and Lyapunov optimization. And to get the solution faster, the mixed integer non-convex programming has been simplified as a mixed integer linear programming, which has been solved iteratively. So this is the overall objective function, where the first term denotes the energy cost and the second term denotes the dissatisfaction cost due to the load curtailment, and all the offline benefits like the long-term energy cost reduction, the security constraints of frequent switching of the capacitor banks or multiple tap operations of the voltage regulators. These constraints are for the rolling time. So we have considered for a real time, it has been considered the time average constraints on stochastic functions. To get rid of this complexities, first the overall problem has been linearized first. Then with the help of virtual queues, we have get rid of this time average stochastic functions, and then after using the Lyapunov functions, we are getting the final linear mixed integer linear programming. So the object is the nonlinear or non-convex constraints are linearized with the help of McCormick envelopes, and the quadratic equality constraints has been linearized with the first order Taylor series expansion. Then this four Qs has been defined to mitigate the effect of this time average stochastic constraints, which will take the effect like when we are saying that at each time interval we trying to reduce the overall tap changing operation or to minimize the effect of the multiple switching effects of the capacitor banks. Then we are just proposing a virtual queue which will increase with each tap changing operation, and with the help of Lyapunov optimization, if we include this term in the objective function, then the minimization of tap changing operation will automatically restrict the multiple tap changing or switching operation. So as we have linearized the quadratic terms with the help of Taylor series expansion, which is mostly dependent on the initialization of the initial point. So to vary the initial point in the multiple iterations, we have proposed this successive MILP solution approach where the Taylor series, where the overall MILP iteratively for multiple times with the solution point we have received from the previous iteration, and it will terminate until and unless we are not getting any updation of in our solution. So case study has been done with the IEEE 123 bus system with four cases, and we can see for the output cases when we are using for the case 4 when you're using both CVR and DLC. Obviously, we are getting the lowest peak demand and the lowest energy loss or power loss in the network. That is the 21.13% of peak load reduction and 19.08% of loss reduction. And to validate the power flow output, which we have received from the iterative solution, to validate that solution, we have put the control variables value in the OpenDSS, and we have got the more or less nearly power flow solution. So we can say that it is converging to the nearly global optimum. We cannot say it is a global optimum because we have done so many approximations, but as we are getting the solutions very fast, then it is quite effective. Then the phase voltage unbalancing rate, obviously, if we are doing CVR and demand response at each and every phases, then it will increase the unbalancing rate. To minimize that effect, we can see with the blue curve. If we don't consider it, then the unbalancing rate is very high. But if we consider it, we can restrict it, then it is quite low. And with the iteration, we can see that the Taylor series mismatch, that is the total error value, is reducing with the rolling iterations, and it is most nearly zero at iteration 4. So comparative analysis is done with different load mix conditions, like to see the effectiveness of the residential customers in a network. We can see that if we increase the percentage of the small commercial consumers, we can see the peak load reduction is less, and also the load curtailment or the load curtailment is lesser because the commercial customers are mostly strict about their consumptions. And if we compare our article, our method with the offline, like day ahead study and the online greedy algorithm, we can see that our technique is obviously it is taking more cost from the offline technique, which is obvious. But for the online greedy technique, it is taking more cost. But as the constraints of the offline, like the tap operations of the voltage regulators and the capacitor banks, for the offline, it is obviously very less because you are forecasting all the events. But in case of greedy algorithm, it is very high because every time we are taking the decisions for that instant only, neglecting its effect on the future. But in our case, as we have considered the future effects in our real-time optimization, so it has somehow restricted the multiple operations of the voltage regulators. And for this IEEE 123 bus system, the overall solution time is around 5 minutes in for our workstation with 8 GB GPU system. This will vary with the system configuration computation facility. And with this, I will conclude my talk. Thank you. If you have any question, you can ask.
Great job. finishing on time. So thank you to our speakers for being very good about their time. So obviously they're students and researchers and not faculty. We're not very good about being on time at times. So, all right. There's one question, and you may want to change the screens. There you go. You see the question. Thanks. You should plot some sort of Pareto front in MOO problems. The first assumptions often used in any game theory problem is individual rationality, which may not always be true. Did you find if any participant in your problem is not rational or associated impact?
For the Pareto, we can do that, but I have not investigated this because I have converted the overall multi-objective problem to a single objective problem. And for the assumptions, obviously there is a rationality problem will occur if we go with the multiple very large number of consumers. But here we have considered for the simulation case studies, and now we are trying to mimic it with the real time with so many different type of consumers. It is only of residential customers of our own campus. The data is taken from them. So definitely it will cause some of the problem if we go with the larger like 10 or 20 or 50 consumers, then it is somehow this technique will be restricted because it maybe it is not at that time also it is not doing justice with some of the consumers. It may happen.
Great. Are there any other questions? I don't see any hands raised. I know we had some earlier questions on part 1. Any other questions? And your information is already in the chat. So I don't know if you have an additional paper you want to share in the chat. Oop, is there a question? Oh, thank you. You're a step ahead of me. So, well, great. Thank you for all those that were able to participate this morning, US time, and this evening. Before we end, I would like to share that we will meet in about 10 hours. For our next session, session number 3, which will be themes 4, microgrid and active distribution systems. And we will have 4 talks this evening in that particular area. And then tomorrow morning, or at the same time, we will finish theme 4 and also have some talks on theme 5, which is cybersecurity. So we appreciate everyone's participation and particularly the students and researchers for their talks. Very interesting, and hope our Indian colleagues have a good evening, and for our US colleagues have a good day. We'll see you later tonight. Thank you.
Thank you.
Thank you, everyone.